let's begin applying these derivatives to some applications. We're going to begin in section 1 with related rates. Introduction. If related quantities are changing over time, because that's pretty much how things change, that's kind of the definition of time is change. The rates at which the quantities change are also related. For example, since a circle's area is related to its radius, then if the circle changes size at a particular rate, the rate of change of the area and the rate of change of the radius are related in some fashion. So you might think of this example like let's say we had a pond, right? And we threw a pebble in. Right, and it made a splash. Then what's going to happen is these ripples are going to, you've seen this before in water, ripples are going to go outwards. And so what's happened is there's two rates of change that you could, well, maybe more than two, but the radius is something that's changing, right? The radius is kind of traveling outwards, probably at some kind of linear rate as these waves travel outwards at a constant rate. But the area is not changing at the same rate because the area isn't like, just proportional to the radius. Right, because the area is growing at a different rate, and so you need to know a relationship between the two, and the area is related to the radius of a circle by pi r squared, right? The area of a circle is pi r squared. So we're going to see through this section how things are related as they're related, how their rates are related. So let's see, sample rates translated into calculus speak, right? So this is kind of an important setup. So number one, the area of a circle is increasing at a rate of 6 inches per minute. So when we look at these units, I'm sorry, I said inches, square inches. Square inches is a measurement of area. So we could write that as dA, or change in area. And minutes is a measurement of time, which we put dt for t is time. So we'll commonly use capital A for area and t for time. Okay, so that's something we could think of there. 2, the volume of a cone is decreasing at a rate of 2 cubic feet per second. So this one's not written out yet. Let's write it out. So decreasing, right? That's going to be a negative. So negative 2 cubic feet per second. In terms of just pure calculus speak, we would say that that's the same as, let me not put an equal sign, right? Same as also, another way to say that is the change in cubic feet is a change in volume, so we'd put dV for volume, and the change in seconds is still a change in time. So in this case, instead of dA dt, I would say dV dt is negative 2 cubic feet per second. That's another way to write it in calculus speak. So number 3, when discussing a circle, dC dt could mean what? Well, I mean, we already talked about dA dt would be the change in area, and you might notice that capital C could mean several things. But if we think of a circle and the letter C, we probably think of circumference, but we can examine the units for more. Notice that the units are inches, so not square inches, not an area, but rather just a length. So it's likely to mean it's the dC dt equals 2 means the change in circumference per second is 2. All right, number 4. When discussing an angle of elevation, we might use theta, like d theta dt. Angle of elevation, you might remember from your trig class, if you have sort of a horizontal and you have an angle. So this angle upwards right here would be our angle of elevation. Could be changing at pi over 4 radians per second, meaning that this angle is increasing, right? So this angle is kind of traveling outwards that direction. And so that's what that can mean, radians per second. All right. Implicit differentiation is how we will get at the use of related rates. So we're going to be applying some word problems and ideas with what we already know about implicit differentiation, and then applying the units as well. So let's get started. For each problem below, differentiate with respect to t. This might be something new. We've been differentiating mostly with respect to x. We're going to be doing it with respect to t because t is what's going to be changing. Time is the key here. So let's take a look at how to do that first before we get to the word problems. So this particular example, we're just talking about the area of a circle. A equals pi r squared. So we're going to take the derivative with both sides with respect to t. So this is going to feel just a little bit different, but it's going to feel similar at the same time. On the left-hand side, you might think of, we're just taking the derivative of a, or the derivative of x, or the derivative of y. It's just one. One what? Well, 1, but remember we're going to use the chain rule, so when we're taking the derivative of a with respect to t, we're going to have to write dA dt. That's going to look very similar to earlier when we did dy dx. Okay, on the right hand side, we also are going to have that because we're taking the derivative with respect to t, but there's no t, there's an r. So first, let's use the rule. Pi is just a constant multiplier, so r squared, we're going to use the power rule, bring the power down and reduce the power by 1. But then you're going to multiply that by dr dt, the derivative of r respect to t. Again, use the chain rule. So now we have a dA dt on the left and a dr dt on the right. Okay, so you can do more, but I think that's good enough for now. What we know is dA dt, that's the change in area given time, is equal to 2 pi r times the change in radius given the change in time. So what we basically have is a relationship between how the area of a circle changes given how the radius is changing. So we're going to use that later in a word problem. Why don't you try it with the Pythagorean theorem? Pause the video. Okay, maybe take a look at that. Remember, the Pythagorean theorem is if you have an a and a b, it can be either side of the legs, and a c, the relationship is a squared plus b squared equals c squared. If we take the derivative with respect to time of both sides of this equation, let's see what we get. So, on the left-hand side, using the power rule, we get 2a, but we're going to have a dA dt, because again, with respect to t, plus 2b tb, oops, not 2b, dB dt. On the right-hand side, 2c dc dt. All right, and there it is. That is our relationship for those three sides. In other words, as any one of the three sides changes, the other two sides will change as well. And so you have to know at least 2 out of 3 to be able to know anything about a triangle. And that's still the case even if we're talking about related rates. Volume of a cylinder, this is something you need to know, but if the volume of any shape that is acting like a prism, a cylinder acts like a prism, so we have a circular base, right, with a given radius r. And if you take that up a certain height, this is probably not the best picture ever, but height would be the height of the cylinder. Then the volume for this is just pi r squared. And where that comes from, pi r squared is the area of the base. Right? The base is a circle times the height. So it's basically the area of the base times the height. In general is what you do for any prism, and a little geometry there. But what we want to figure out is how are these related given a change in time. So we're going to take the derivative with respect to time of the left and of the right. Now on the right hand side, you're going to have the product rule. We have pi r squared times, a little invisible times, h. So make sure you're using the product rule. Okay, here we go. Derivative of the left. Derivative of v is 1, so we just have 1 dv dt. On the right hand side, let's use that product rule. Derivative of the first, power rule, 2 pi r. Don't forget your dr dt. Times the second, h. Plus the first left alone, pi r squared. Times the derivative of the second, 1 dh dt. And there's our relationship between how the volume of a cylinder changes, given how the radius is changing, and given how the height is changing. That's that relationship. Now you're going to see how this plays out later in the video when we have actual numbers and setup situations. Okay, so now a little more practice with this kind of manipulation. For the following exercises, find the quantities for the given equation. A, find dy dt at x equals 1 if y equals x squared plus 3 and dx dt equals 4. Okay, we've got a lot of given information. I think the place to start is to notice what the equation is. Okay, so that equation is given as y equals x squared plus 3. So if we grab that equation and consider its derivative, let's start there. We're going to have the derivative, and if we want the derivatives with respect to t, we're going to of course have to do d dt of the left side is equal to the derivative with respect to t of the right side. Okay, on the left side, the derivative of y is 1 dy dt. On the right, the derivative of x squared is 2x dx dt, and then the derivative of 3, that's a constant, so it's 0. So there's our relationship. Now this problem, what we're actually asked to do is find dy dx at x equals 1. Well, I'm sorry, I said that wrong. Find dy dt. Well, we have dy dt right here. But the problem is we know that x is 1, but we don't have dx dt unless they give it to us, which it is given over there. So now we're just going to plug in. We have 2. We're wanting it at x equals 1. Plug in 1 for x. And then dx dt we were luckily given as 4. So our answer is 8. Okay, I want to give you a chance to practice yourself, but before you pause the video, I do have a typo. Please fix that on the right hand side. This should say dx dt equals -1. Otherwise, you won't be able to finish that problem. Okay, go ahead and pause the video and try it. Okay, if you tried that and you found the derivative of this, you should have learned that dy dt is equal to 4x dx dt. Plugging in the values given, x is given as -2, that's there, and then dx dt, I had to change that, right, is -1, so you should have had 8. All right, hopefully you got that. Let's go ahead and take a look further. Let's see what's going on with my... Okay, moving on to this next page, we're going to look at setting up and solving related rate problems. And here are some steps, but again, I think it's better than memorizing the steps, is just kind of understanding the process. Number 1 is to assign the symbols to all variables involved in the problem and draw a figure if it's applicable, draw a picture. 2 is write that equation that relates everything in step 1. So after you've labeled everything in step 1, right, you have all the variables labeled. You're going to have to find an equation that uses all of those variables. So whether it's the Pythagorean theorem or the area of a circle or the volume of a cone, something. 3, use the chain rule and differentiate both sides of the equation in step... whoa, that's a typo right there. Several typos here. In step 2, with respect to the independent variable, which is usually time, as we've done thus far, right? We did derivative with respect to t. This new equation will relate those derivatives. And then 4, you're going to substitute all known values. You might have to do a little solving along the way if it's not given to you completely. And that's the note here. When solving a related rates problem, it is crucial not to substitute known values too soon. That's crucial. If you plug in all of your numbers at the start, basically you can turn an equation into a constant. When you take the derivative, it's just 0. So don't do that. Don't plug in the values until after the derivative has already been taken care of, unless there's a really good reason to. And I'm going to try and not share any of those reasons. All right, example 1. So the side of a cube increases at a rate of 1/2 meter per second. So here's a picture of a cube. You might imagine the side length, meaning this length here. Here I have it pictured at 4 meters. And then it's increasing in 8 inches per minute, or I don't know what that's all about right there. Let's just get rid of that. So 4 meters. Find the rate at which the volume of the cube increases when the side of the cube is 4 meters. All right. So we have a couple things going on. We have the side length of the cube, right? And that's going to be increasing at a rate of 1/2 meter per second. So let's start there first. Let's write that in calculus. The side increases at a rate of this, meters per second. So if the side is increasing s, we're going to call that ds dt for the increase of the side, and it is equal to 1/2 meter per second. So we have that down already. So, but again, we had to kind of translate what that meant. And then we're trying to find the rate at which the volume increases. So we have to relate the volume to the side. And perhaps you already know that, and hopefully you do, that the volume of a cube is just found by multiplying all of the dimensions together. In this case, if it's a cube, it would be s by s by s, and that would be s cubed, right? S times s times s. So we're going to take the derivative of that equation. All right, so let's do that with respect to t. So the derivative of the left side, the derivative of the volume, the derivative of the right side, s cubed. The derivative of v is 1 dv dt equals power rule 3s squared ds dt, and that's an s. You got to make sure you know that's an s and not a 5. That's very important. All right, so now that we have what we want. Find the rate at which the volume increases. That's this piece right here, when the side is 4. So let's plug in all of the values. We have 3, right? We have s squared. The side is now 4, so it's 4 squared. And then we already were told in the problem ds dt, came from over here, is 1/2, and that goes here. Just evaluating, 4 squared is 16, and maybe do this left to right. Half of 16 is 8 times 3 is 24. And then I think it's very important to apply the units. And the units are what we're talking about here. We're talking about this dV dt. A measurement of volume is cubic, so this is cubic meters per second, right? We're just basically taking the units we had over here and just rewriting them in terms of the volume. So to read this, to restate this in English, what we would say is when the cube is exactly 4 meters in length on each side, and the cube side is increasing at a rate of 1/2 meter per second, then the volume at that one point in time instantaneously would be changing at a rate of 24 cubic meters per second. So it basically tells us how the volume is changing per how the side length is changing. There's the relationship. Let's take a look at some other examples. I like to think of this one as when you blow up a balloon. You might have noticed when you blow up a balloon that when you first start blowing up a balloon, it seems to increase in size really rapidly, but when the balloon gets larger and larger, every time you blow into the balloon, it doesn't seem to be changing much. And that's because the radius starts to slow down given a constant volume change. In other words, if you're blowing the same amount of air in a balloon, eventually it doesn't look to be changing much in radius because the balloon is so large. So we're going to examine that here a little bit here. So you can see in time, right, that in time 1, that if the volumes change at a certain rate, the radius might slow down. So here's the setup. A spherical balloon is being filled with air at the constant rate of 2 cubic centimeters per second. And there's an extra 2 there. Not sure what all the typos are doing in this problem. In this set of notes. Let's cross that out right there. All right. So we have to translate that. A spherical balloon is being filled with air at the constant rate. Let's examine the units. What are cubic centimeters? Well, that is a volume. So I'm like, okay, that's a change in volume. And then the other unit, what are seconds? Well, that's just a change in time. So what we write in calculese is dV dt is 2 cubic centimeters per second. In other words, the change in volume of this spherical balloon is the rate. How fast is the radius increasing? How fast is the radius increasing? So the question really is, what is dr dt, right? The change of the rate of the radius when the radius is 3 centimeters, and that's when r is 3. So we need a formula that relates the volume, which is kind of a number we're given, with the radius is what we want to find. Well, you hopefully know this formula, but the volume formula for a sphere is 4/3 pi r cubed. That one's good to commit to memory. It's pretty common in mathematics. And it has a beautiful proof if you take that in geometry class, but we're not going to get into that here. So now we're just going to take the derivative with respect to t of both sides. So on the left-hand side, derivative of v is 1 dv dt. On the right-hand side, well, let me go back a second. Let's do it. 4/3 is just a constant multiplier, and pi. But when we take the derivative of the r cubed piece, we're going to use the power rule. So don't use the product rule because pi is not a variable. It's just a constant. So all of the 4/3 pi is just a constant. Bring the power down and reduce the power of r by 1. And then times, don't forget dr dt, because we are taking the derivative of this with respect to t. All right, so we have all the elements. Now let's plug in everything we know. We were given earlier in the problem that dv dt is 2, so this is a 2 on this side. Okay. I noticed some simplification, and maybe you already noticed it, that this 3 and this 3 can simplify. And so we're going to get 4 pi r squared. And we were told in this problem that r is 3. We want to find that, right? So we're going to plug in 3 squared. And dr dt is exactly what we're trying to figure out. So I'll leave that there as the unknown. Let's move our work over here. So we got 2 equals 3 squared is 9. 9 times 4 is 36 pi dr dt. And dividing both sides by 36 pi, we have our answer here. dr dt, the change in rate and radius given a change in time, is 2 over 36 pi, and the units for radius are given as centimeters per second. All right, there we go. The key there is knowing that formula for the volume of a sphere. So get that one down. All right, this is a very famous calculus problem. I think it's in about every calculus book I've ever seen. A 10-foot ladder is leaning against the wall. You can see it pictured here on the right. If the top of the ladder slides down the wall, that would be bad. Like imagine you're standing on this ladder here, and the top of the ladder, this point right here, right, begins to slide down the wall. That would be really, really bad. You'd be about to be in trouble on the ladder. It says the top of the ladder slides down the wall at a rate of 2 feet per second. How fast is the bottom moving along the ground? In other words, when this top comes down, right, when this comes downwards for us like that, then the bottom of the ladder is going to slide outwards. All right. So the question is, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? So we're told that at this one point in time, we know that this distance right here is 5. Okay, so we're going to have to find some sort of equation that relates this 10-foot ladder to these changing distances along the wall. And you might see it right off the bat, but this looks to be a right triangle, right? So let's label it. If this is A and this is B, and the hypotenuse, it would be C, but C is given as 10. In this case, we don't need to write C because, well, remember I told you earlier, don't plug in the variables too soon, but if you notice that the relationship is the Pythagorean theorem, a squared plus b squared equals c squared, you can go ahead and plug in the 10, because in this problem, what's changing? A is changing because the top of the ladder is sliding down, and B is changing because the bottom of the ladder is sliding out, but this 10-foot ladder remains a 10-foot ladder. It's not going to change. So dc dt is 0. There's no change in the length of the ladder. Anyway, here's our formula. Let's say that you didn't plug in the 10. You were behaving yourself as a calculus student and said, no, I'm not going to take any chances. I'm going to plug in later. Let's go ahead and do the derivative with respect to t of both sides. And we'll go back and examine what's happened in the problem in a second. So, derivative a squared to a dA dt, b squared to b dB dt, c squared to c dC dt. We've already done this once before. Great. Now let's go back and read the problem. Well, what do we have? Well, a 10-foot ladder is leaning against the wall. 10 feet. What's that? That's my C. Plug that in over here. 2, 0. All right. But what's dC dt? That means the change in C, the change in the length of the ladder given time. How much does the ladder change in length? It changes none. So that would be a 0. So on the right side, you just get a 0. Because it's 2 times the length of the ladder, 10, times the change in the ladder, none. There's no change in the ladder. But up in the problem, we were given a rate. It says if the top of the ladder slides down the wall at a rate of 2 feet per second. Now, what does that change? That changes the value of A. A is going to be whatever it is here, right? And it's going to be shrinking. It's going to be going down. So we would say, let's write this in calculus, that the length of A is changing at a rate of 2, but it's shrinking, so negative 2 feet per second. All right, so let's plug the values into the problem. We have 2 a dA dt. Well, we know dA dt, we just learned, is negative 2. That's what we were talking about over here. But we don't have the value of A, but we can find it, because if we look at our triangle over here, we have a situation right now where this is 5, right, that's what it said, and this is 10, and so A can be found using the Pythagorean theorem. A squared plus b squared equals c squared. And then 100 take away 25 is 75. So A would be the square root of 75, which I believe would be 5 square root 3 if you simplify that. And so that's the length of A. I'm going to insert that in here for A, 5 square root 3. And then plus 2B, and B we know right now is 5. dB dt. Now, we aren't given that, but that actually is the question. How fast is the bottom moving along the ground, right? That's B. How fast is the bottom moving along the ground? So that's my dB dt. And if I solve for that, I have it. So I have this equation right now, and I can just put all the numbers together and see what happens. So I've got this first term. That's going to be 2 times negative 2, negative 4 times 5, negative 20 square root 3, and then plus 10 dB dt equals 0. Add 20 root 3 to both sides and divide by 10. You get 20 square root 3 divided by 10, and that's my change in B. And it's going to be the same units, feet per second. So as the top of the ladder is coming down the wall at 2 feet per second, that's what that negative 2 is all about, the bottom of the ladder is sliding outwards at a rate of 20 square root 3 over 10 feet per second at that point in time. Crazy, but you can actually find these relations. Let's take a look at an elevation change. A rocket is launched so that it rises vertically. A camera is positioned 5,000 feet from the launch pad. So the distance from here over to here is this 5,000 feet. When the rocket is 1,000 feet above the launch pad, that's my distance here, its velocity is 600 feet per second. What's velocity? The rocket, right here. This rocket is going at 600 feet per second. Okay, it's probably worthwhile right now to translate what that means in calculus. What does that mean? It means that the rate of this elevation change, of this height, will be changing at 600 feet per second. Let me notice again that this looks to be like a right triangle. So we could use A, B, and C, X, Y, and Z. It doesn't really matter. I'm going to use this as A, and I'll just label this as B. So this part here in blue is a change in B, right? The change in the B value over time right at this moment is given as 600 feet per second. And it's going to be a positive because it's increasing, right? The rocket's going up. Find the necessary rate of change of the camera's angle. Oh, the angle is theta. So we want to find the change in angle, or in other words, d theta dt is what as a function of time so that it stays focused on the rocket. In other words, as this rocket goes up, this camera's got to change at just the right angle, and that angle is changing over time. So what we have to dream up here is we have to dream up an equation that relates all of the elements in the problem. Typically what students do incorrectly here is they start like, oh, right triangle, let's go with the Pythagorean theorem. That's not going to work because we don't have to relate A, B, and C, but whether we have to relate A and B and the angle. That means we have to think about trigonometry. If we look at this angle and we look at the sides given, what are the relationship of those sides given that angle? And hopefully you can notice that this up here would be the hypotenuse. We're not given any information about that. But this would be the opposite side, and this would be the adjacent side. So of the things that I've highlighted in blue, the angle, the adjacent, and the opposite, the equation that comes to mind is tangent. Tangent of theta is equal to the opposite over the adjacent, and I have it labeled as B over A. All right, and I know that B is 1,000, but again, don't plug in too early because B is changing. Great, there is our setup. Now, if we want to figure out d theta dt, we're going to have to take the derivative with respect to time. So let's do that. d dt, both sides. On the left side, the derivative of tangent is secant squared theta. Don't forget to multiply with using the chain rule. D theta dt. On the right side, let's use the quotient rule. Derivative of the top, that's dB dt, 1 dB dt, times the bottom, a, minus the top, b, times the derivative of the bottom, dA dt, over the bottom squared, a squared. Okay, so we got a lot going on here. What we need to do at this point, now that we have this derivative fully knocked out, is we need to plug in all of the information that we have. Let's see what we have and what we need to get. We have B, for sure. B is 1,000. We do not have A, unless it's, oh yeah, I'm sorry, we do. A is given as 5,000. That's a constant. Oh, and that means also that we have dA dt. So there's a couple things to think about here is that if A right here is given as 5,000 feet, dA dt is how much A is changing over time. Well, this camera stays here on the ground, and this rocket is going straight up, so this length of 5,000 always stays the same, and that means that's 0. So good, we have some elements, right? We have A, we have that value, and we have dA dt. We have all of that taken care of, and we can plug all of that in. The other things that we need are B, and we have that given as 1,000, dB dt, and that's given up here as 600, and we have the elements here and here. Great, we have all that we want. On the left-hand side, however, the question, remember, is what is d theta dt? On the left-hand side, all that's left is to figure out what the angle is, because we have to figure out secant squared of theta. Now, if we look over here at the problem, you can see we do not have theta, so we'll have to do a little bit of work for that to find theta, and we're going to get that in just a second. Okay, let's start with plugging in what we have, what we know. Let me just undo these reds and what kind of lines, and we'll do them one at a time. So let's write it. On the right-hand side, we have dB dt, 600, times A is 5,000, minus B, that's given as 1,000, times dA dt, and that's 0, over A squared, 5,000 squared. On the left-hand side, d theta dt, here, we still need to find what is theta, because we need to find secant squared of whatever theta is. Let's go find theta. How are we going to do that? we're going to use a little trigonometry, all right? And that's because we know the opposite and the adjacent, and we know that the tangent function, that's what we started with, is equal to the opposite over the adjacent. And that means that theta is tan inverse of that, 1,000 over 5,000. Great, that is our angle. Now if we're going to plug that into this problem over here on the left, we probably want to use a calculator to figure out that value and do some approximation. So let me use a scientific calculator to do that. Okay, so I used Desmos scientific calculator to approximate that. I just went over the Desmos and I made sure I was in radian mode, tangent inverse of 1,000 over 5,000. I'm going to round this off. I'm going to call it 0.197. I think that's a good approximation. So 0.197. That's the last element of what I need. Oops, the last element of what I need to plug into my equation for this value of theta. So let's go ahead and plug that in into our equation. So it would be 0.197 goes there. And so now we just have a bunch of evaluation. I'm going to go ahead and go back to Desmos. I'm going to type in all of this on the right. I'm going to type in secant squared of 1.97 and get some decimals. Let me pause to do that. Okay, I typed that in. Let's take a look at it. So on the right hand side, I have this line of 0.12. So this right hand side, let me go back over there. Let me scroll down just a little bit. This right hand side is 0.12. On the left-hand side, I had to figure out secant squared of 0.197. That was a little troubling on Desmos because it doesn't have a secant key, but I just used the reciprocal of cosine for that. So I did 1 over cosine of 0.197, and then I squared it because it's secant squared. I got this value of 1.0398. I'll just use that. 1.0398 d theta dt, dividing both sides by 1.0398. Again, we're approximating here. Then d theta dt is approximately, going back to Desmos, I did that ahead of time. This bottom one, I'm going to just round off to 0.115. That's an approximation, so 0.115. And I did this all in radians, so this would be radians per second. A lot going on with that problem, so meditate on that, rework through that one. Okay. The last problem I want to look at in the notes here is this one about a cone. It's an upside down cone, an evaporating cone. The setup is a container has the shape of an open right circular cone as shown in the figure. The height of the cone is 10 centimeters. You can see it's labeled, and the diameter is also 10. The water in the container is evaporating so that its depth, h, is changing at the constant rate of -0.3 centimeters per hour. All right, so the height, overall height, is going down like that. And so let's just label this in calculus. It says the depth is changing, so that's dh dt. All right, that's key right there. All right, so in other words, this water is going down because it's evaporating. A, find the volume of water in the container when h is 5. So I don't need any calculus for this. I'm just finding the volume, but I do need to know the volume of a cone. So the volume of a cone is very similar to the volume of a cylinder in that its base is a circle, and you can do base times height, but when things come to a point, there's a 1/3. So the volume of a cone, this is cool to know. Volume of a cone is given by the formula volume equals, so it's the same thing, pi r squared, that's the area of a circle, times the height, but then you're going to do 1/3 of that because it comes to a point. All right, so we want to find the volume when h is 5. So let's plug in 1/3 pi radius squared, h is 5. Now it's tempting to just say that the radius is 5, because if you look at the diagram off to the right, you can see if the diameter is 10, that this of course would be 5. But we're being asked about when h is 5. So it's more like this diagram of the shaded part. When h is 5, what is the radius here? Well, there's a nice, sorry about that, there's a nice relationship here, is that since the height, right, of 10 is matching the diameter, that's going to stay proportional. So we can just use reasoning. If the height is 5 of the shaded region, then the shaded region in question would have a diameter of 5, and that would mean the radius is 2.5. So I'd put 2.5 squared in there, and that would be my value. I can approximate this. I'm just going to use a regular handheld calculator. Don't forget to do the order of operations. 2.5 squared times 5 times pi, and then divide by 3. I'm getting it's approximately 32.7. That's an approximation. 32.7 cubic centimeters. No calculus at all, just literally plug it into the problem. Okay, let's take a look at this last part. Find the rate of change of the volume of water. Rate of change of the volume of water. Let's translate that into calculus. That would be change of rate of volume given time is what we want. So we're definitely going to be using that formula from above. That's volume is 1/3 pi r squared h. Okay, with respect to time, when h is 5. Okay, so before we get started, we need to do a little bit of work, and here's why. If I look at this equation, I have an r and I have an h. So if I were to take the derivative right now, I would be using the product rule, and I would also end up with, don't write this down yet, by the way, don't write anything down. I would be ended up with some kind of dr dt there, and over here I'd have some kind of dh dt. But if you look back up at the problem, you'll notice that although they gave me the change in height given time, I don't have that at all. So I would be out of luck. I would be kind of stuck. So let's make our life easier and avoid this error at the same time. And that is, we're going to look for a relationship between r and h, and then I can make this a function of just one variable rather than two, and I will no longer have to use the product rule. Let's go look at the picture. So I was kind of talking about this before, but let's just write it down more clearly. What we have is this relationship that whatever the height is, it's always matching the diameter, and then the radius is half of that. So let's write that down algebraically, is that the diameter is equal to the height. The diameter really is made up of 2 of the radiuses, so 2r equals h. That's what we need. Let's take that little joyous fact way back down to our problem, is that 2r equals h. Okay, so we can look right here and see that we could plug in 2r for that h. However, I want to remind you before we do that, let me write down this fact first. 2r equals h. If we go back up to the other given piece of information here, we have dh dt. We do not have dr dt. We don't want to get rid of h and I'll have r. Instead, we're going to want to get rid of r and have h. So let's do one more step here. If we divide both sides by 2, another way to say it is the radius is half of the height. That's what we want to plug in here. So we don't want to get rid of the h, we want to get rid of the r. Let's see how this would look. The volume will be 1/3 pi r squared h, but r is half h. That'll go in here. Okay, so let's keep going. 1/2 h squared, 1/2 times 1/2, 1/4, h squared, h. Let's clean this up a little bit. So we got 1/3 times 1/4 is 1/12 times pi. I'll just write it as pi over 12. And h squared times h is h cubed. That's my new v. Great. This is my updated formula. The volume is equal to pi over 12. That's just a constant, h cubed. In other words, I have a function now with only h and no r. And now I can do my derivative with respect to time of both sides. Let's do it. All right, on the left side, dv dt, that's what I want, right? I want to know dv dt equals constant multiplier, just leave pi over 12. Now let's use the power rule. Bring the power down, reduce the power by 1, multiplied by dh dt. Let's plug in everything we know about all of those. All right, so pi over 12, 3, h squared. We're given that h is 5 here. Great. And dh dt is the piece of information that we were given above. It's -3/10. They're highlighted. So we're going to plug that in here. And that is our answer. If we just simplify this out a little bit, probably look a little bit cleaner. Let's see what we can do here. See, 3 goes into 12 4 times. We get divide by 5, divide by 5, if I'm not doing anything incorrect. So we have 3 times 5 left, -15 pi, and then the denominator, 4 times 2 is 8. That makes sense as far as the sign, because if the height is going down because it's evaporating, then the volume would also be going down, and this would be in cubic centimeters per, hour. All right, so that's the change in volume at that particular rate and time. Okay, see you for more in class.